Goeie. Ja, nou hoor ik hem.
Okay.
Okay, sorry. So in 1984, this guy who knew everything from this Campbell soup company, he was recorded. All the rules, the many tricks that he knew were all recorded. And he retired, but it actually didn't work. After some time, there came new valves and new things, and it was impossible to keep up all these things. So in the, let's say, 90s and so, artificial intelligence died, and nobody was actually that much more interested in it. And we did classical computer vision and computer-aided diagnosis and machine learning. And how does it typically work? Mitko already told it a little bit. You have a test set and a training set. You train the whole system. You do pre-processing, you do some segmentation, you do feature extraction. Feature extraction can be all kinds of things. Find edges, corners, histograms, curvature, locally binary patterns. There are so many feature detectors, but people design them by hand, and today we learn them. That's the big difference. Then you do feature selection, and this feature selection is in this feature space. You have to find classifiers that divide the feature space, and Mitko already said that we have now more fancy classifiers. And you store the features, then you have some smart classifier, and there are dozens of classifiers. Mostly, you know these classifiers. You have support vector machines and Adam classifiers, you name it. And the final class is that you say it is tumorous, sorry, or it is non-tumorous. So the classical machine learning applies lots of filters. A very famous one is Gabor feature filters. Cluster them in feature space, and then you have a validation. This is called the receiver operating curve. The more it is to the upper left, the better it is. So you have the false positive rate against the true positive rate, and 100% correct you can't reach, but you always compare, let's say, the curve that humans have and that the machine have, and the one who's more to the left is better. Okay, classical. But now we have these neural networks. And why are they called neural? Because the weights that we see in these neural networks are the synapses in the neurons. We're going to look more out to synapses, how they self-organize, how they grow and shrink, and so on. And we already know that if you use a synapse more and more, it gets bigger. And that's actually how the brain learns. If you forget, a synapse shrinks and can also completely disappear. And you have quite a number of synapses. You have 10 to the 10th of neurons, and every neuron has 1,000 to 50,000 synapses. So you have billions and billions of synapses. So the artificial model is sum them all up, threshold them, and you get some output. And then people made these neural networks, and normally they had an input layer, some layer where the processing was done, a hidden layer, and an output layer. So the classical one was 3 output layers. You put in a lot of images, and you say, well, what is it? Is it the cat? Is it the dog? But these networks only gave about 75 correct. And for a long time, all this computer vision work was more or less, people are always so much better, so let the computer vision do their work, but let's wait until they come, and now deep learning, it finally works. And the big breakthrough came in this competition. Can you classify from 1.2 million images in 1,000 classes what the image shows? It's the ImageNet large-scale visual recognition competition. It started quite some years ago, 2010. 1.2 million images, and there were 2 requests: localize objects in the image and detect. Localization in 1,000 and detect in 200 categories. And it was actually working quite well. And if you see what happened is, in 2010, it was a shallow layer. The error was 28%, 2011. But look here, in this year, 2012, we had a major jump from 25 error to 16 error. And this was getting the big attention. From this moment on, everybody said, hey, what is this deep learning? And we are middle in the revolution right now. The guy who wrote this wrote a net that's called AlexNet, and we go in detail see what is AlexNet doing. It was with 8 layers, and here it was improved. And now we make more and more layers. And now we have 152 layers, and we are at 3.5%. Actually, this was 2015, and we have even better. So it goes tremendously fast. But how do you choose how many layers? How many choose how many parameters in all these nets? What's a net actually doing? It's a cascade. So it is a deep only means, Mitko already said, because we have so many layers. From the input layer, you have a first layer of simple things. So here we see very basic feature detectors. It's called edges, but it could be edges, lines, very simple things. And now we see that we go to more complex things, so you need context. If you want to detect a nose, you need 3 edges, one here, one there, and combine these 3 edges, so it's not a local operation anymore. Features only work on local operations, so we need to go many pixels further. How do we do contextual mathematics? And if you combine these objects, or parts, noses, eyes, and so on, you have to combine them again. So you take the next contextual area, and now you get objects, and then you get groups, you get persons, and so on. So you make it bigger and bigger and bigger. And what are the mathematical steps that happen here? And what are the steps that the visual system is taking? Here we see the visual system, it's the eye. It goes to the thalamus in the middle of the brain, and then it goes to the back of our eye, of our head. And a quarter of the brain is for vision. That's amazing. A quarter of your brain is for vision. So we are really visual machines. We have hundreds of millions of filters right there, and all kinds of connections and feedback loops, and we go study in quite detail what happens. There are several signals coming from the retina, and we will see how these signals work, and we will see that the retina is completely not a digital camera. We have rods and cones, but there are 26 different signals coming from the retina, all different tilings. It is a multi-scale. It has histogram of gradient detectors in the retina. It has velocity detectors. It has a very specific color analysis. So it's completely not a normal camera. And we're going to look at why is this camera needed to do really good perceptual grouping, to do really good, let's say, deep learning. So we are still, I think, too simple in deep learning. There's much more to come. And I want to use this course to give you some ideas and hope that you can continue on these ideas. And the way we see now self-organization is that all these weights here, and we have quite a number of weights. In a deep neural network of today, we have millions of weights, sometimes hundreds of millions of weights. And how do you know the weights? Well, people say you just learn them. You start with random weights, and you put in some image, and you look at the end, is there an error? And then you adjust all the weights until the error is 0. And then you do it again and again. And that actually works. So you update by an incredible amount of data putting in there. You update all these weights. But that's actually pretty stupid. You have to learn this. And the training, it takes forever. Training a good network sometimes takes weeks or sometimes months if it's really big. And you need a lot of data. Can we do this faster? Well, we're going to look at how could this be done faster. Can we go from supervised learning to unsupervised? It's not so easy. So we need large sets of training data. We need a clever network architecture because this is quite plain. And Mitko already showed you that you can have branches, you can have feedback loops, you can have all kinds of different networks. So what architecture do you take? How many filters do you take here? How many layers do you take? There's so many options. How is error backpropagation working? And you need, at the end, a robust classifier. Lots of questions. So the idea is actually context, and this is the notion of context. You see an image here, Beamer is not that bright, but you see a catheter here. This is an X-ray from a chest. And the X-ray goes into the heart, that's somewhere here. And if you do a local detection, you see locally this. And actually, there's nothing to see here. But if I give you the context, you see much more. You don't need to see this point, which is almost invisible. And radiologists always make bad pictures. They make just as good pictures. Because if you take good pictures, you need a lot of radiation. And radiation induces cancer. It splits water molecules in these OH1 and H+, and these are quite aggressive radicals. So this is context, and this is actually a science that already started in the 30s. And people looked at, people are pretty good in context. So if you see these groups, you see actually 3 lines here. So this was called the principle of proximity. And this was called the principle of similarity. They have the same distance here, but now they are different. And you see horizontal lines. And you see enclosure. You see symmetry. And there were a lot of laws were actually found, and these laws were called Gestalt. So the group of psychologists who work on this were the Gestalt psychologists. And people never managed to get the mathematics of Gestalt. And only today we see a little bit what this Gestalt is doing. And that's exactly what we need to understand the next layers of deep learning, because that is exactly what deep learning is doing. Deep learning is not looking at features. Features means it's a local thing. What's the curvature here? What's the edge? But Gestalt means, how can I look tens or hundreds of pixels away? What is my further away neighbor doing? So we go do a little bit different mathematics than the usual ones. We have continuity, what happens here, connection, what is the ground or what is the figure. You see 2 faces here, but you also see a vase. You have to make a kind of a choice. And all these Gestalt laws, we're going to inspect a little bit more deeper, but then in a strictly mathematical way. So what's a deep convolutional network do? 2 passes. You put in the images, like Mitko said. You have a lot of training data. And this deep neural network is organized that all the network connections are measured. You start, however, with a fixed architecture. So you say, I start with 30 layers. I start with 48 filters in the beginning. And these filters are 7 by 7 and so on. You train it. And once you have a trained model, that's the goal. That's actually, you have built an expert. So if you have this model, it's very expensive, and we will show later in this course that these models can be downloaded. Mathematica connected a lot of these trained models. And we have dozens of these models, and it's super to work with them because they are an electronic expert. Then you have the testing. Is it really working? So you say, okay, I put in lots of images of which I know the ground truth, and you make tumor probability maps. So this is the detailed architecture of AlexNet. Let's have a look. It's a convolutional neural network. So it works with convolutions. This afternoon we have a computer class, and you can train a little bit what is the notion of convolutions, how does it work with boundaries and so on. But I guess that all of you know how convolutions work. What is the mathematics? Yeah? If people don't know, then this afternoon we can study some more. So we have an input image, and this input image is 224 by 224. And we have some filters here, kernels or templates, it's all the same. And that is the filter that shifts over the image. That's the convolution. It's 11 by 11. And you get one output here, and it is projected here. Well, we have quite a number of these filters. We have 48 of these filters. So this first filter scans the image. It makes layer 1 here. The second makes layer 2, and have 48 layers. And this is no longer a matrix. This is now called a tensor. That's what we have, TensorFlow and so on. We're going to look at more complex data structures. Well, why do you take 48? Why not 43 or 21? It's all open. And what I see a lot of computer vision or computer scientists do, they play. and they do heuristics. They just say, okay, let's try 21 filters. Let's try 22 filters. Let's try 23 filters. And everybody's doing the same. So all these hundreds of laboratories, they try. What's Google doing? They say, well, we automate this. We make AutoML, and you can just say, run it, and the system itself tries 21, 22, 23. Super. But it is no understanding. It is heuristics. It is a little bit, it works in some sense, but I like to understand a little bit what's really happening. So we have a huge block of data here, and we go do a next convolution. So every layer here has a next convolution. So this guy is now 55 by 55. Why it is smaller? Because they said, well, let's not take every pixel a step, but we take every 3 or every 4. So we go a little bit faster over the image. That's called a stride. So you can make a bigger step convolution. Okay, but the images, the data explodes. So we have another filter. Now we take a smaller one, 5 by 5. We project here. But because it is getting so big, we say, okay, let's take a 5 by 5 max pooling. Max pooling means nothing else than, well, we have some output here, but only the highest output is the most relevant. So let's take only the highest output. So from every 5 by 5, 25 pixels, I take the maximum one. It's called max pooling. You do a convolution again, you do again max pooling, you do a convolution again, you do again max pooling, and so on. And then we have a classifier. It's called a fully connected layer. And I'll discuss that much more in detail next week. And then at the end, you get an output. And in this case, we had 1,000 different classes. And 1,000, a class means is the cat, a dog, a church, a house, a beach, whatever. So the processing is from simple lines to more complex. And you see the context complexity increasing here. And in the end, you get the output. This was the jump from 75% to today, 94%. And it is in two ways. Like Lego, you can build up all the different stages in your deep network. And we have fantastic software to do it. And tomorrow I will explain how in Mathematica you can program line by line all your convolution, max pooling, and so on, line by line. And you just build your neural network in just a few lines. You train it, and it works. So it's a little bit like Lego. And of course, you have to train it with checking if everything is all right. So you say, OK, if the output is not right, I get some error. So we have to define a cost function or an error function, and then update all the weights until this is right. And that updating goes fast. And we have some nice tools to do that. And a typical big neural network has hundreds of millions of connections or weights. So has the brain. So we need to do a little bit of physiology of the brain. And of course, you know about the retina and so on. But you don't know about what is V2 doing, and what is V4 doing, and what is the mediotemporal doing. So we have a lot of stages here. And today, people know exactly what they are doing. They are incredibly well researched. The visual system is the most researched brain area. And there are hundreds of laboratories now measuring what happens in mice, in rats, in monkeys. So there's a lot of different techniques to measure in the brain, especially optical techniques. We cannot see a single cell, but we can see hundreds of cells. We can see population firing. And we see what these stages more and more do. Until the first few stages, we understand pretty well what happens. And here it gets more enigmatic. So Mitko already said we need big data. We need a GPU. That's a game card. And actually, a GPU is now available in every computer. This laptop has a quite big GPU. This afternoon, I will show you how to measure in your own computer what is the performance of your GPU. And we have these deep neural networks. And of course, we have cloud computing. We rent today all these GPUs from Amazon or from Google. And you can just order 1,000 GPUs for a week, and it's pretty inexpensive. So it's very easy to do. You don't have to have your own big machines. You just take a subscription to the e-cloud of Google or whatever, and you have massive computing power. But training takes a lot of time, and the training is the big thing. And getting data from doctors. Doctors have no time, doctors are expensive. If Philips needs to have training data from hospitals, they have to pay the doctors so at night they can do the validation of all these things and do the ground truth. And sometimes data sets cost hundreds of thousands of euros. It's pretty expensive. We have the challenges now, so lots of data sets are available on the internet. But if you're a professional company and you need, I don't know, 10,000 MRI sets, how do you get them? You need to collaborate with the doctor and say, okay, you diagnose 1,000 sets for me, and I pay you. So be prepared that pay for data. It's very expensive, and the doctors are getting now aware of it. They no longer give you the data for free. They say, well, you actually buy my brain, and you take my job, so you should dearly pay for these data. That's coming up. And they are now taking all kind of legal preparations. Well, what's a GPU? That's actually a thousands of parallel cores. It's coming from the game industry. You have to generate 60 times per second beautiful 3D worlds, and the CPU was not good enough. So today we have, for example, these GeForce cards. This is a box that I recently bought for the group last year. And it has 8 NVIDIA Tesla XP GPUs. That means 8 times 3,600 cores. That means 29,000 cores. 29,000 processors. That's a lot of processing power. And it's incredibly cheap. I paid $30,000 euros for this. That means €1 per core. That's nothing. So you have a supercomputer for a very low price. Not for you at home, but for institutes, this is very, very cheap. But otherwise, rent them. And the normal, you have already quite some hundreds of cores in your own laptop today. They're very affordable, so these big, this box, this card alone was 1,200 euros. And then you have almost 4,000 cores. They have big memory, 12 gigabyte, and you can block them in big groups. An example of big data is, of course, all we know, Google Photos, but let's see a little bit how big is big. And why is it free? Well, Google stores a lot of data, and if you see how much data, it is 3.7 petabytes. And a petabyte is 1,000 terabyte, so this is a lot of data. So they give it for free. And why? Well, they use it, of course, for training their network, and with this network, they earn a lot of money. They have, for example, Street View. Why do you photograph hundreds of millions of streets? They do it for free. That was very expensive to drive these cars with all these cameras around. But now they're very happy because if you have a self-driving car, they have Google Street View inside. So that car sees a house, and he doesn't see, okay, that's a house because it's the windows. I know it is that house. So he knows exactly that is Ricardo Street number 17. So I know where I am, and I know from which angle it is. So it's getting quite tricky. They know everything. If you see, here you see some statistics of Google, and it's interesting to follow those statistics. I'm not going to show this in too much detail, but Facebook and so on, they have the same. So you have some statistics here. How many Google Photos users? 500 million. 1.2 billion photos updated every day. 1.2 billion every day uploaded. If you want to get data, what's the best way to do it? Make a service like this. And Google does it. And the winner takes all. So if you're big, you win. And that's why you see all these big companies, they become bigger and bigger, and they win. There are no second Googles. We had Netscape, we had Firefox, all the other ones. They're gone, more or less. So we see that more and more. If you have big data, you win. So let's have a look at an example here. This is my own photo collection. And it's called Google Photos, so we go to Google Photos. I was in meeting Santa Claus in Utrecht. I wanted to get some paper notes. But let's search. let's search to something, rhinoceros. I was in the zoo some time ago, and now it finds all my pictures with rhinoceroses. So I was here in the zoo, and it finds also statues, and small ones. It's quite amazing. It finds all the... Here, this is a ring of my wife. So it is pretty impressive. And this is done by deep learning. So if you have 1,000 by 1,000 pixels, or 2,000 by 3,000, whatever, how do you find the rhino? Well, that's actually what... And you can type anything here, and it's amazingly good. I did a big project over the last years to study the detection of diabetes, and in the last week I will give a big overview of that. And we used deep learning, and we looked at diabetes, because with diabetes your blood vessels begin to leak. The high levels of glucose, they interrupt the connections between cells and blood vessels, and they get leaky, and the blood vessels get weaker, they get more sloppy, they get wider. And working, you see the blood vessels better than in the eye. So we took images from the eye, and TW was asked to assist in China, where 11.6% has diabetes. Many people don't know. So we decided to do a big project, and we're going to screen 24 million people. That's the other half of one province in northern China. And we set up a project, and we had an amazing project. 4 PhD students, 10 master students, 50 publications. It was quite nice. And what we did was detect all kinds of early warnings, exudates, changes in blood vessels. And we used a quite nice network, which you see here. And we go explain it in more detail. Here you see more what has happened. This is the original image. And you need to find all these, what's called exudates. These are the leaky deposits that come out of the blood vessels. And for doctors, this is a nasty thing to find out. How much is there? You cannot count it. It is difficult. And we found a method that we say, well, we don't want to have a doctor annotate all these different areas. No, we just say, there is something. So we had the input image-based, but the system gave it back pixel-based. So the pixel was classified as its exudate or normal, but the input was just, there is something. So it was much easier for the doctor. Well, this was done by residual nets. And we're going to talk what are residual nets. A couple of examples, and this afternoon you can show them further. I go quickly through this. NVIDIA is the main supplier of all these game cards. They have a news page or a blog page, and every day it's updated, and it's an amazing series of what are new applications for the next generation of vehicles. All kinds of applications with deep learning. It's a very interesting news site to have a look at. You all know Google TensorFlow. It's free software that you download from Google, and you can see it's now 1.12, and everything is here. It has classes, it has software, it has introductory tape, and so on. And lots of companies are using it. It's very famous. I'm not going to talk about how to use TensorFlow. You can easily do this yourself. We go talk a little bit further. Well, this is interesting. AutoML, that is actually, it does it all automatically for you. If you have a data set, plug it in, and AutoML automatically sets all the variations. So it changes the filter size, it changes the number of levels. And it's wonderful to read. This was a guy, he said, well, we have 41 ramen shops, and ramen is a kind of Japanese noodle. So we have 41 cooks, and they all made, it was one brand, they made the same ramen, but a little bit different. One was cutting the meat a little bit thicker, one was putting the meat on the side, the other on the top, etc. And he took several hundreds of these pictures from 41 ramen shops, and they classified it, and AutoML, that 48,000 pictures, get 94% accuracy that they could point out, okay, this plate of ramen was from that shop. That's quite amazing. And AutoML did it all automatic. So if you have data, download AutoML and you're done. but you don't know how it works. Another site I really want to recommend you is medium.com. That's a kind of, it's a journal, Scientific American style, and it has lots of topics. It has also a topic, artificial intelligence, and it has a lot of explanatory articles. So it gives exactly a very nice, for example, one guy writes, I took a course and I explained how, they explained how backpropagation was working. It took me a long time, and I write now for you how that works. So they summarize these kind of things, and it's quite nice. So have a look. You have to search a little bit. It's quite big. I'll give you some examples during this course, but it's highly informative. Kaggle.com we already saw. That is the challenges. But Kaggle is the general challenges. Mitko talked about the medical challenges in biomedical imaging. And Kaggle is a company in California, and they give money. And some years ago, they had the first diabetic retinopathy detection. And we said, wow, they had 100,000 grant money, winner money. And you see that 661 teams were joining, and they gave 90,000 retinal images for free, 30,000 to train, and 60,000 for you to find out. And people subscribed, and here you see the leaderboard that were the winners. And we also joined, and we got 17 from 661. That's not too bad. It's in the best 2.5%. The first three, they had to give their code. So all the deep learning code was open, and everybody studied, of course, their code. That's the reason why the companies pay this money, because you have the money here for, let's say, 2 people for a year. That's nothing for these companies, and they get all these people working for you and generate the code for you. So it's a very easy way. So if you want to earn money, go to Kaggle, and Kaggle has today lots of these data sets. So here you see the Kaggle competitions, and they have, I don't know, it should be in the order of hundreds. And just pick out customer revenue prediction. Have a look. Oh yeah, this was I saw yesterday. This is the first artificial intelligence newsreader. And it was made in China. And this is an avatar, but it is so incredibly good that I'm not sure if you... No, it's not incredibly good.
Hello, you are watching English news program. I'm AI news anchor in Beijing. Panama's participation in the ongoing China International Import Expo is showing its...
etc. But automatic news lasers are coming up. So deep learning is getting everywhere. So if you talk about generating fake news, this is a super way to do it. It's scary in a sense. And there's so much coming up. And you will be the generation who will be in the middle of it. And there is a lot more coming. Who invented this? 3 major guys who wrote together a famous Nature paper, and you really should see this Nature paper. It's called deep learning. It's fantastic. It is the basis of these inventions. Geoffrey Hinton is a very good scientist, gives beautiful lectures. He's in Canada. Jan LeCun, you have things called LeNet, and that's all from this guy, Jan LeCun. And you have Andrew Ng. How do you pronounce this, Chinese speakers? I don't know. It's a very short name. He was for a long time with a Chinese company, Baidu, but he's now head of the Facebook lab. Let's take a couple of simple first steps to see what happens inside. And we're going to look at supervised learning and multivariate linear regression. So a typical application is a classification. So you have, for example, images of handwritten numbers. And this is a very famous data set. Every computer scientist takes this. It's called MNIST. You have some generic learning mechanism, and you specify what's the number. Or emails, is it spam or not spam? And let's predict the price of a house. And very, very simple. we have a list, and 3 bedrooms, square feet, what is the neighborhood, a noble town or a hip town or Skid Row, Dull, and this is the price. And now we have a new house, can we predict the price? So what we do with supervised learning, we have to have a lot of examples and figure out from these examples what is actually the connection, what is inside. And if I ask you to do it, you can easily say, okay, I have to make some combinations here. 2 plus 4 minus 5, no. 2 times 4 minus 5, yeah, that's right. So it is 2 times 4 minus 5. So if you have a couple of them, what happened in your brain doing that? You can solve it. You just make all kinds of combinations and you find it. So you need not one example, but you need a couple of examples. So that's why we need a whole bunch to train. So let's now do this for the house. Is there any pattern? And we have some code. So we say we start with a house price that's 0. And we say, okay, the average house price is 200. So we say 200 per square feet. And if the neighborhood is quite hip, we make it 400. And if it is a Skid Row, it's 100. Let's just give it some initial data. And we start with a price based how big the place is. So we have the price per square feet times the square feet, and that's the price. And the number of bedrooms, well, if it is 0, then it's cheap. So the price is 20,000 less. And if there are more bedrooms, we say, okay, it is the price plus $1,000 times the number of bedrooms. Some very simple rules. Can we configure out this? So we start with we start the price at 0, and then we say, okay, the price is the number of bedrooms times, yeah, let's give it a weight. And I really don't know the weight, so I give it a random weight. And the price is added by the square foot times another weight for the square feet. We really don't know, but let's give it a random number. And the neighborhood, we give it a random number. And at the end, we add a kind of a basis term, that's the bias. So we have random weights. So now let's see what happens. That turns out to be not so, these rates are a little bit crazy, so let's start with a weight set to 1. So we put all these weights now to 1. And now we have a learning set. So we know the sale price from this house. So we say, okay, we have here 250, but my prediction with these weights of 8 gave 178,000. So it's wrong. This was also wrong. It's pretty close, but not really good. So you need to make an error, and the error is actually always what you put in and what you get out, you take the difference, but you don't want positive or negative, so you square the difference and you average it. So that's called the cost, or the error. The average error, because you divide it by, you make it the mean. And in machine learning, you write it like this. It's just the output minus the input, square it, you take the mean. And this error, you have to minimize this cost function, so you want to go to the minimum. And if you want to try lots of different combinations, you say, okay, I can try every combination, and if I have here 10 by 10 possibilities, you have 100 possibilities. You calculate all of them and you find the minimum. That's a lot of work. So people normally say, okay, I start here. I only calculate my neighbors here, and I see, if I see, let's say, left, right, behind, and before, what my neighbors do, I want to go down. So we only take going down, and that's called the gradient descent method. And you start here, and you want to end up in the lower, and then with the gradient descent, you see that the further you reach the 0, the better you get your fitting line. Well, this is called multivariate linear regression. And of course, you can make this as fancy as possible. And Mitko already said you can make many, many more layers. If you have just a few layers, you have a linear. Here you have a little bit more quadratic, and you can make it 5th order, 4th order. This is called overfitting. How do you reduce that? So it actually works like, take some inputs. This is from Geoffrey Hinton, one of these slides. I go quickly through it. At the end, you have a threshold function. Normally, threshold function is the sigmoid function. It has this formula, and that actually says it is saturating to 1 here and saturating to -1, to 0. If you plug in this, you have the inputs here, and you have the weights. You multiply them, you get 21. So this is now my input set, 3 numbers, and these are the classes, so I have lots and lots of these rows. If you put the input set here, you get the output. It is not 0, it is 0.8, so the error is 0.8, and you update all the weights. You do the same. This should be 1, it is 0.9, so the error is now -0.1. You update the weights, and so on. Many, 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 many times. And next week, if we have done a little bit more basic mathematics, I go exactly in detail, explain to you how this backpropagation works. Because this is quite a complex mechanism. What's the brain doing? What are the mathematics of this? If you have a network like this, there are beautiful demos. This is the guy who was a PhD student at Stanford, and he wrote convolutional neural networks in JavaScript. So you have deep learning in your browser here. Lots of demos. And the most famous demo of all is MNIST, handwritten data sets. Who of you have worked with MNIST? Half of you, I guess. Yeah, quite a few. It's a typical toy data set to start deep learning. You can download it from a website. It's very small. The images are 28 by 28 pixels. And tomorrow you go do it yourself with Mathematica, and you train your network, you build your network, you change it, you download the data. It's all very easy. Let's have a look at this network. So this is it's actually already running, and you see it takes 1 or 2 milliseconds. It is now training the network, and in the meantime, it is looking at the error. So you see, the longer we train, the error gets smaller. It is already 0.44, 0.31, and we have already seen close to 2,000 examples. You have some lines of codes here, and now we see what the network is doing. So here you see the input, some gradients, and this is the first convolutional layer. So it has 8 filters, and what are these filters doing? And you see, it looks a little bit like edge detection. It has some derivative detection. It has derivative in x and y, so it's doing some very simple operations here. Then you go to the ReLU, that is the rectifying linear unit. We will show that in a minute. And you can see level by level what's happening, and it's not clear what happens here. This is, yeah, very much noise. And you see how well is it working. Green is that it's working actually quite all right. So simple network, in a few minutes, it trains quite well. And have a look at the other examples yourself. Well, all these weights, they have some mathematical representation. W is weight, and we have here 4 plus 2 neurons. We forget about the input, so we have 4 here and 2. We have so many weights and so many biases, so we have 26 learnable parameters. That's already pretty high-dimensional space, but we go to millions. These are called the weights, and these are called activation functions. An activation function is actually what is the relation between output and input. So we can have very complex activation functions. They take in a vector of input, weighted by all the weights, and they give out an output. And you need to have a non-linear activation function, finally, so the network trains into a very complex thing. So with 300 neurons, you can get these kind of things. With 6, you can get this. And there is a whole list of activation functions. If you look on Wikipedia, there are actually lots of them. I will show only a few. You have the identity function. You have the binary step function, you have the logistic function, the tangent hyperbolic function, the arctank functions. Only these first few I will use in our experiments. But there are quite a few. People have done very, very fancy things. But most of them, you see that they have a relation between input and output. This is the most used one. It's called ReLU, rectified linear unit. So that means positive signals go the same and negative signals become zero. This is a very easy function to implement. And because it is so easy and it is so cheap, it is far better than what neurons do. Neurons take this sigmoid function, if you measure them carefully. Okay, so what's the sigmoid function? 1 divided by 1 plus e to the minus x. This is the tangent hyperbolic function. And this is the ReLU function. This is much faster because it is so easy. The function is quite simple. It's x for positive, and it is this guy for negative. Sorry, it is 0 for negative. People have also made a leaky ReLU that say, okay, we should take it a little bit, this negative, so we take the maximum of 0.1x here. So there are some variations, but we mostly take this one. And I talked about overfitting. If you have too many variables, it gets like this. Okay, we also have something like dropout. People say, well, we got so many things, let's forget about it, and we just do not take all these connections, but we decimate. We take just a few of these connections. It turns out to be working quite well. So this dropout, what's the mathematics of this dropout? Well, later we will see, actually next week, that it's very equivalent to blurring. So Gaussian blurring, that regularizes. If things are very bumpy, then it's quite normal to regularize it. There are also lots of loss functions. And the loss function means what is the, if you have classification, how do you get the output? And we will look at a lot of softmax and cross entropy. It looks a little bit complicated right now, but this is an introductory lecture. I want to give you the features, and next week, or tomorrow already, we go in detail. What do they really mean? Okay, we said training. I already did this. Look at the time because we need to speed up a little bit. So we have this convolutional neural network, lots of weights, forward and backward. And how is this actually going to work? So next week, we study all the weights here. We take a network like this. And then you see all this mathematics coming up with derivatives. It's quite complex, but this is just a preparation that we're going to explain this in great detail, what's working here and what's happening. So I scare you now for, wow, this is coming up. I'm not going to explain it right now. We need some preparation and build it up. We have enough time. We have 24 hours of lectures coming up. So after this lecture, we go really slow and build this up step by step. And finally, yeah, understand it. And actually, it makes sense. It's actually quite simple. And this we do in week 3. So these work with convolutions. We all know what convolutions are. You have to be careful that if you take a convolution like this, you see that the input is 5 by 5, and the output is 3 by 3. Normally you want the same, and you see that the step size is every 2 pixels, so be careful, you have a stride of 2 here. If you want the same output, you have to do something with the boundaries. So people say, put zeros at the boundaries. It's actually stupid because there is no 0 at the boundary. Suppose the image is high and here it is 0, you introduce a jump. So it is wrong. Then people say, okay, let's extend with the mean. Then you make a less jump. Still wrong. So there are many things you can also do. The reflection, what some people do, you say, okay, I flip it the other way around. So I don't have a jump at the border. But everything is wrong as long as you are aware of it. You should know that the convolution integral is this integral. This is the filter, and it moves over the function f. And you should know that the convolution is the filter moving in the negative direction. So tau is the shift. And you see that it is shifting all over the place from minus infinity, all on the left of the image, to all the right. You can interchange this. You can move the filter or you can move the image. It's both the same. And there's also something very similar. It's called the cross-correlation integral. It's doing exactly the same, but now it moves in the positive direction. So you have to define, if you program, if you do correlation or if you have convolution. With correlation, you shift your filter. With convolution, you flip it and you turn the other way around. So this is quite important. We can also do this in the Fourier domain. As you know, that convolution is indicated by this operator. So I have a filter and I have a function, or a function and a filter, doesn't matter. If we take the Fourier transform, that's always with a capital. So the Fourier transform of f is capital F. This convolution becomes now a product. Super. Very easy to make a product. Much easier than this convolution shifting all over the place. So what we normally do is we say, okay, we have this guy, we make all the Fourier transforms and we calculate f, because we know h and g, and we have this, we take the inverse Fourier transform and we get our result. These are a lot of pointers, tutorials, the famous machine learning by Andrew, and I want you to look in this yourself because I want to do this in this course. There are lots of tutorials. This is from Machine Learning is Fun, Coursera. There are so many, and have a look this afternoon or later this week in all these, what's available. So let's start this first lecture by summarizing what these convolutional neural networks do. We need to figure out how big should we take this, 11 by 11? What actually happens here? Why do we take 96 levels in our tensor here? So it's still a black box. There was a nice message here. And I think I got it in my recent advances for a better understanding of deep learning. And this guy said there was a big, in Stockholm, international conference on machine learning, 5,000 participants, 629 papers. Deep learning theory has become one of the biggest subjects of the conference. And all these people were talking, what is towards theoretical understanding of deep learning? It is the big issue of today. So in this course, I hope to have a lot of discussions with you. What could be the trick? What could be the real, and people talk about non-convex optimization, over-parameterization, the role of depth, generative models. So this is how the community is looking at it. And in this course, we take a little bit of a different approach, the brain. So that's why I appetize you a little bit for what's coming up. So tomorrow I go spend the morning. The first lecture will be fully on the retina. The second lecture will be on the cortex. And the third lecture will be how to implement these things. I stop here, and we take a little break. And I'm going to talk a little bit in the next hour on Mathematica, because we use that as a play tool with all the concepts I'm going to discuss. This lecture was an overview of what are the basic building blocks, what's convolution, what are these value layers, actually things you all know. It's pretty well known, I guess. But you have now seen a little bit the big picture. But it's very much magic. We still don't know how they get organized. So let's go a little bit deeper. In the next hour, I give you the first example of some neuromathematical first principle reasoning. Okay, let's have a break and get back in 10 minutes.